Hello, my name is Emily Timpe. My group mates are Nick Lodder, Grace Angles, and Ryan Griffin, and this is our process intensification final project. For this project, we have integrated 2 of the 4 domains of process intensification into a TDI debottlenecking process. The domains we have integrated are the functional domain and the temporal domain. The functional domain focuses on increasing process efficiency by combining one or more functions into a single step. This often maximizes the synergistic effect, which is a key property of process intensification. Examples of equipment that can improve a process in the functional domain include a monolith stirrer reactor, a microstructured reactor, and a divided wall column, which is the piece of equipment that we have chosen to integrate into our process.
There's an opportunity to use a divided wall column in the distillation train of our TDI process simulation. These 2 columns are used to first remove phosgene present in the stream and then remove ODB, which stands for the orthodichlorobenzene. In this example, phosgene would be component A, ODB would be B, and TDI would be C. In the first picture, the side draw location of B is shifted up because the boiling point difference is largest between ODB and phosgene. Therefore, less column height is needed for the separation of these 2 components. In the second picture, it demonstrates that we would also shift the wall closer to the feed side of the column, since the mass flow of ODB is expected to be considerably higher than the other 2 streams. Here are 4 reasons for using this method of process intensification. The first one is that we would eliminate the need for 2 columns. The second is the defos column would be retrofitted with the divided wall. We could also expect to see lower total energy usage and take up less real estate within the plant.
So the temporal domain addresses the amount of time that it takes for the process. A shorter residence time is generally ideal for the processes because the throughput can be increased and energy consumption may also be reduced. The plate heat exchanger reactor that we will be mentioning a little bit later has excellent temperature control in the reactor, and some mixing inherently will occur, so both of those will have a positive impact on the residence time. Finally, in the article that we researched, they state that the silicon carbide is 6 to 20 times more efficient in heat transfer, which brings us back to that last point of excellent temperature control, but this time specifically regarding the material of construction, which may be able to reduce the residence time as well.
Okay, so speaking more on the silicon carbide heat exchanger reactor, so it shows high corrosion resistance, silicon carbide plates, as well as high thermal conductivity and low relative roughness. So this is very favorable because it's very efficient heat exchange. It shows similar properties to aluminum. It offers that high corrosion resistance that aluminum doesn't. And so as you can see in the table, both the overall heat transfer coefficient and the performance indicator is at 6 to 20 times greater than the compared to the other heat exchangers. And so we would like to implement this equipment into the process that was discussed earlier, the phosgenation of toluene diamine to make toluene diisocyanate. There are 2 reactions that have to take place. One, it starts with the jet reactor, and then it moves into a hot tower, as you can see in the picture below. And we would like to replace the hot tower with multiple silicon carbide heat exchanger reactors in parallel. So this would reduce the overall volumetric consumption of the equipment. And it would also combine, obviously, both heat transfer and reactions simultaneously. And would also offer, we suspect that it will offer reduced residence time since we have parallel equipment and it doesn't have to go all the way through a tower. And so our references are right here, and we thank you very much for watching our presentation. Thank you.